Hi guys, welcome to Learning Electronics Repair. I have a storage oscilloscope here from FNIRSI. This is the 1014D. This product's been around for quite a while and it's been reviewed several times by several people. But they asked me to take a look at this, particularly from the point of view of this channel, which is a repair channel, to see, is this any good for repair work? So let's open it up, let's have a look, let's talk about a few other reviews of this, and then let's prove for ourselves one way or another if it's any good, is it any use, yeah? Here we have the oscilloscope, we have the user manual, we have two oscilloscope probes in there. These are ×1 ×10 probes, standard oscilloscope probes. The little instruction book, we'll have a look later, and the oscilloscope. Also in the box we have a power lead, and this is USB powered. Okay. We have a clip-on oscilloscope probe, basically. And we have what looks like, yes, a USB lead. Okay, A to A male. This is nicely vacuum packed, I guess is the correct description for this. So let's get into this, which is usually more difficult than you might think. And then let's have a look what we have. And here is the oscilloscope. We have the screen protector, so we'll take that off. It's quite light, there's not a lot of weight in this, it's quite slender as well actually. It does have a carry handle. Okay. You can lay this back if you want to do. It has flat at the back, but it may have power at the back. Let's have a look. Well, it has a power socket which is located here, and this fits the USB cable that came with it. So I can't actually lie it flat on its back, but you know what? The only real reason I'd want to do that is because I want to make a video, and it's easier to record this way, yeah? It has little feet, this is the normal thing, I guess. Yeah, mounts nice on the desk. So, all in all, it feels a bit cheap and plasticky, but then this is a sub €200 bench oscilloscope, so it is aimed at that area of the market. Now let's see how we're going to review this. Well, the first thing I will say, FNIRSI have sent me this for free, so I have not actually paid for the oscilloscope, but I have full control over the content of this video. It's entirely up to me what I do with it, how I test it, and what conclusion I come to at the end of it, okay? As I mentioned, there are a number of reviews of this, and I had a quick look around. One of them is a guy, Kerry Wong, makes a lot of videos, a lot of review videos, and he did a review and teardown on this. Various other people did. Now, some reviews say it's really good, they really like it, they think it's an excellent tool. Kerry thinks it's absolutely awful. He says that this is not a 100 megahertz oscilloscope, it's a 30 megahertz oscilloscope, and a number of other things he says about it. Basically, his conclusion is this is total junk, it's rubbish, don't touch it with a 10-foot pole. He also mentions a comparison with his Rigol 1052E, which, funnily enough, I also have one, and says that the Rigol and Owen and similar ones are far superior. So, I thought the best way we can approach this, and as you know, this is a repair channel, is we'll use this oscilloscope in a number of real life repair scenarios, things that we would do during a repair. I'll also get the Rigol and we'll use that as well. We'll compare the two and we will determine whether the Rigol can actually assist us in our repair or detect problems that this can't, yeah? So some sort of fault or some signal where the Rigol would tell us if it's working or not, and this will not tell us if it's working or not. I think that's the fairest way to test that, because at the end of the day, that's what we're doing here, yeah? I look back at one of my previous videos, which had a lot of views on the little handheld scope. So the tests I put that through was originally with an RF signal generator, injecting up to 100 megahertz or even more, and seeing whether the scope will actually tell me if we have a signal or not, because in repair work, that's basically what we want to know. I looked at a VRM, multi-phase VRM on the motherboard, looking at the pulse width modulation. Will this show us whether the phases are working, whether the PWM is working or not? That's another typical application. I will then see if we can check whether a microprocessor or a GPU is accessing the BIOS when it boots up. Very typical use again. And can we capture that BIOS read, if you like? Can we see that it's doing it? We'll test motherboard, 25 megahertz crystal. That's probably, again, one of the highest frequencies you would need while you're actually doing work, unless you're a radio amateur or doing high frequency RF. Admittedly, it's not something I generally do, but I will accept that sometimes you may do that. Okay. We'll check whether we can trace audio signals with it. And we'll look at switch mode power supplies. Can we check whether the MOSFET is being driven on the switching supply? Can we detect the pulse width modulation? Can we see if that increases with the load? Yeah. So we're going to do all those things with this scope, with the Rigol scope, the same that Kerry Wong used. And then I think we will have to prove A, is this actually a useful tool? Or B, as Kerry said, is it total junk and useless? Yeah. The oscilloscope is supplied with a power supply. That's this one. It's rated 5 volts, 2 amps. Now they do mention about this power supply in the manual, so let me just show you that. We have here in the start of the manual then some serious warnings. That's probably the best place to put them. When the two channels are used at the same time, the ground clamps of the two probes must be connected together. It's strictly forbidden to connect the ground clamps of the two probes in different potentials. This is very normal, especially the different potential terminals of high-powered equipment. Otherwise, the oscilloscope motherboard will be burnt. Because the two channels are grounded together, connecting to different potentials will lead to a short circuit of the internal ground wires of the motherboard. All oscilloscopes are the same. That's correct. So basically, it's telling us that we have two scope probes and each one has a ground clip. You cannot connect the ground clips to different places on the circuit board that you're taking the measurements from, unless those different places are actually electrically connected together. For example, two different ground points on the motherboard. So that is absolutely correct, and that is normal for any oscilloscope. Let's have a look what else we are being warned about. The B and C input of the oscilloscope can withstand 400 volts at most. It's strictly forbidden to input more than 400 volts in the position of a 1 times probe. That again is normal. I would usually keep the probe set to 10 times, which effectively sends a voltage 1/10 of the measured voltage into the oscilloscope. So in other words, if you connect your probe to a 400 volt signal on the board you are testing, 40 volts reaches the oscilloscope. And this is absolutely normal. 3. The original power supply must be used. It's strictly forbidden to use the power supply or USB of other devices under test. Otherwise, the motherboard ground wire may be short-circuited during test. What this is telling us is that this power supply has internal isolation from the mains, unisolated 240 volts, and the 5 volts. To be honest, that's probably true of most USB power supplies and similar power supplies, but we specifically know that this one does have. Possibly it has greater isolation than a normal transformer. So for example, between the high voltage hot ground side of a power supply and the safety ground, you would have isolation from the opto-isolator and the feedback circuit, and from the insulation of the windings of the switch mode transformer. But it's possible to make switch mode transformers with better insulation characteristics. For example, windings on two separate bobbins around the same former, rather than one winding over the top of the other, will give greater insulation. So I'd like to think, without opening this up, that they are saying that the isolation between hot ground on this one and safety ground is very good, but I'm assuming it's going to be at least as good as you would normally expect from a switch mode power supply. This is important because on our oscilloscope probe or probes you have a ground clip. And here we may have a ground. This one doesn't have. I mean, there's no ground pin. Okay, fair enough. But if your ground clip is connected to the safety ground on the main side, not the low voltage side, when you connect this to the device you are testing, you are connecting wherever this goes to on the board to ground, earth, yeah? If that happens to be a power supply with hot ground, then as soon as you connect that to earth via a power supply, things are going to go bang, yeah? Probably the device you're testing, the test equipment quite possibly, depending on the path across the PCB of the ground where the current goes, and it's not really conducive to your own, shall we say, you may need a new pair of trousers. Yeah, that's the best way to put that. So that is a very important thing, and it's nice to see that this is stating this has isolation from safety ground, which means we can connect this scope probe to anywhere on a hot ground, on a power supply switch mode, for example, quite safely. Having said that, there is a caveat, and there often is, isn't there? So the caveat is that when you connect this to hot ground, you're effectively connecting it to live and neutral via the bridge rectifier diodes, depending on which half cycle of the mains. This is live or neutral, and it's changing 50 or 60 times a second. So this is basically a high voltage. That also applies to this part of your scope probe, that part in there, and this part here, and these parts, okay? So, although it's relatively safe to use this sort of oscilloscope for probing in live mains circuitry effectively, you do need to know what you're doing and understand there are still hazards. As long as you know what the hazards are, this lot, the casing, I'm sure you're safe to touch. This lot, you're not, yeah? So just know what you're doing. The same would apply if you connect a USB lead here to something, I don't know, a computer to monitor this. Well, you've created an earth path again. Expect bad things to happen. Okay, so a quick safety talk. Now let's switch this on. I've plugged the power in, touched the power button, and it powers up, of course. So we have a very nice display there. The first thing I will say is how clear that display is. That's really nice. I'm just touching the scope probe. It's working. Okay. I'm going to try mainly the single channel use of the scope on this video. We may have a little play with the dual channel later. But having had a quick play around with this to save myself from looking stupid, I can say it's quite easy to use this, at least in its basic use, which is probably what we're going to do in repair work. So we have a signal. This changes the amplitude of the signal. This changes the position of the signal on the screen. This is the same controls but for channel 2, which we're not using at the moment. And this is the time base. So effectively you can see we can alter the horizontal scale, basically the time base. Okay, so the frequency of the signal is the same. You can see on the screen there it's 50 Hertz, but it's just altering the display that we're seeing. Okay, 50 Hertz. We can alter the position on the screen. These are all standard settings for oscilloscopes, and this last section is the trigger. So we can go into, for example, single. If you look at the top left of the screen, we're now in single mode. We can set the trigger point. Okay, single will effectively give us one scan till it fills the entire buffer of data. We can now scroll through the captured image. Okay, we can go effectively back to live, just hit mode again. We're back in auto, for example. The waveform's changing as I'm moving on the desk, by the way. So that's the basic use of an oscilloscope. There have been many reviews of this device, so I won't go into the ins and outs of every control on here. The user manual is quite sufficient and there's plenty of reviews. What I really want to do, as I said at the start, is to compare this with my Rigol oscilloscope in a number of standard common repair scenarios and find out which scope will work better in those scenarios, if either do, and to find out if either of them are junk. Okay, let's start. So the first thing we're going to do is inject a signal from my RF generator up to 100 megahertz, maybe more, and let's see what the scope does with that. Okay guys, I have my RF signal generator attached to the oscilloscope. I've clicked the probe on there. So let's power this up and let's see what we get. Well, we have on the generator, I'm sure you can see 7.2 megahertz, and we have a waveform on here. We also have a display that says 7.2 megahertz. And this is quite simple to use, this scope, I think, if you want to look at waveforms. So I'm just moving it up and down quite simply with the control. I can decrease or increase the amplitude of the display very simply there, okay? And the time base, just adjust it, okay? So we have that working quite happily at 7.2 meg. Let's go up to the next preset band, which is simple on this, that's 10 megahertz. And on the screen it's saying 10 megahertz to the right hand side of the display. Okay, we have it. Let's just go again. 11.7, you can see it matches what's on here basically. We'll go up again, 13.7. So this signal generator can go up to about 225. Okay, we have a display with it 17.5. It may be looking slightly jittery, but with electronics repair, basically, what do you want to know? You want to know if there's a clock there or not, okay? That's at 25, 27, 28. Now it's lost the trigger because the blue line, the trigger point, or rather the green line, is not within the waveform properly. So we can just adjust that, just go to normal mode, set the trigger into a better point in the waveform. There you go. You can see the little green T. A little bit of fiddling around with the controls and we have it. Okay, but fiddling around with the controls on the oscilloscope is something I've been doing since the 1970s, yeah. So 50 megahertz, it's saying 50 megahertz. I think the next one probably is 100. Yeah, 100. And there we have it, 100 megahertz. Now, the frequency display is losing us a little bit. That does seem to be the limit. You can see that this is changing around a bit. Let's just go down a little bit from that. So I would say this oscilloscope probably does struggle at 100 megahertz. But it would certainly show me there's a signal there. And that's normally what I want to know. 90, okay? We're there on 90.925, it's saying 90.8, it says, as I say, moving around a little bit. Now I accept that that probably should be more stable. So you can kind of see how the scope is performing at these frequencies, okay? Let's compare this with my Rigol and see how that performs. And here is my Rigol oscilloscope. So this is DS1052E. I've had this since I think about 2014, maybe longer than that. I do know that these can be converted quite easily to 100 megahertz. I think just as simply as loading some firmware with USB actually. But I've never done that with this scope. This is how I bought it. And why? Because, well, it's a workhorse and it's always done what I need. I've never come to a situation and thought, oh, I need more bandwidth. If that happens, I would, okay? But for probably the highest clock frequency I ever measure on the repair is 25 megahertz. It's doing the job. So let's switch this on. Well, the first thing you will note, it takes quite a lot longer to boot up compared to that FNIRSI one. Whether that matters to you, I don't know. I guess probably with an oscilloscope, I don't use them that often, so it's not an issue, yeah. But I'll just mention it. So we have a display on here, it's telling us a frequency, 7.24, jittering around a little bit, as the FNIRSI was. On the generator, you can see it's 7.2, but this isn't calibrated either, so I'll just mention that. Let's go up a few frequencies, okay? This generator, by the way, doesn't give a very good sine wave on lower RF frequencies. This is a little home-built project, basically. We're up now at 14.1. You can see the display on here, so you can see what he's doing. Okay. 21, 26. I probably need to just change the time base now a little bit. Okay. 50 megahertz and 100 megahertz. So you can see my 50 megahertz scope is doing a very good job to 100 megahertz. And it's doing that better than the 1014D was, okay? What's the next band up on this? I don't actually know. 130. This is reading it, yeah? The FNIRSI wouldn't go at 100, it wouldn't give me a reading. How far will this actually go? I've never tried this before, actually. 220, and now it's sort of kind of like not happy with it. Okay, time division's at the limit, so not as high as that, but this 50 megahertz scope is doing rather well. Can you see now, guys, why I've never felt the need to upgrade it or change it, yeah, for what I'm doing with it? I'll just turn it down in megahertz at a time. Okay, it's down at about 208 now. It's still not quite keeping up with it. 205, it's giving a fairly close approximation of that. Triggering it nicely. The trigger was well out of the range, by the way. Turn it up a little bit more. Well, I was being unfair to it, guys, because the trigger wasn't really set properly. Okay, 225. And that's as high as my generator will go, okay? So, you can see a difference. Yes, at high frequencies, this one works better, yeah? Does that make any difference for repair work? Apart from, fair enough, VHF frequency repair and such like. But for what I'm doing, computers, power supplies, audio equipment and similar, does it make a difference? Well, let's find out. The first real world repair scenario then, is a VRM working? Do we have drive to the MOSFETs? Let's have a look. So I'll just mention before I start, and I will do the same on the Rigol, by the way. I have two scope probes attached. I'm not using both channels. One of them I'm just using, you can probably just see it here actually in the shot. Just there. So I'm just using one to clip a ground to my board, which means basically I can then just use this scope probe like so, without having to have a short ground lead. This is okay to do this, by the way, on low voltage stuff. Do not do this on high voltage stuff. Yeah, if you're going to ground it like I've done, take the clip off altogether. Stay safe. In fact, now it's off, I'll leave it off. So, these are the VRMs down here. You can see them in the inset picture. So we're going to have a look to see if these are running, okay? First of all, we need to start our board. Okay, now let's have a look. So I just need to find the V core. Let's see where it is on this one. And it's there. I have a waveform. You can see it's a bit big. Just alter the size a little bit, alter the time base a little bit. And there you have it. So that is the output from our VRM. This is telling us that it's 294 kilohertz VRM, 1.6 volt pulses. Okay, so we can see it's running, we see the pulses there. How does that compare using the other scope, the Rigol? Will it do it any better? Will it tell us anything different? Let's have a look. Well, let's see. I think we can say, unsurprisingly, the answer will be they are the same. But let's see. So we get onto the VRM. Okay, we're off the scale, just adjust it slightly. Okay, yep, there we have it. And it's the same, it's 290 kilohertz, 1.24 volts. So both these tools are going to tell us that that VRM is working, and we can look at all the phases and we can see that they're all working. So yeah, I didn't expect any difference, but they do this. Well, we have the Rigol here. Let's have a look at the system clocks. So we'll look at the real-time clock and we'll look at the 25 megahertz clock, okay? And then we can compare, of course, with the machine we are reviewing. So the real-time clock is here. What do we have? Well, we have a clock, okay? We have a clock, a little bit of jittering on it, but there again, there's probably noise from the power rails. This is only 30-40 millivolts. The frequency is telling me 33 kilohertz, but it's varying a little bit. Let's go up to that one. Try the trigger. Well, it's telling us 32 kilohertz. Okay, I'm going to switch the power off. Yeah, and that's clean now. So that noise is coming from the power supply and the motherboard, basically. So we have that one. And then the 25 megahertz clock. Let's see where that is. Well, on my board, that's actually over here. What do we have? Well, we have something. Let's just increase the time base. Try again. I'm on the wrong pin, my fault. Okay, so there we have it, 25 megahertz very clearly displayed on the scope. Okay, so we can say that clock's running. We know because the motherboard's working, but we can say visibly that's running. Let's try the FNIRSI now to take these two measurements. First one then, we'll go with the real-time clock, which is over here. You can see the crystal there, hopefully. Alter the sensitivity. Okay, we have a signal there. Alter the time base. And it's there. So this is telling us it's 32.7 kilohertz. In fact, it's actually doing that a little bit better than the other scope was. It's telling us 192 millivolts, 182. I didn't actually check that on the other one. Okay. But it's certainly doing the job fine. Okay. Let's go for the 25 megahertz clock. So that is up here, as we know. I'll use my left hand, so I have my right hand free for the scope. Let's have a look. Okay, and that is showing it. Again, 25 megahertz. Okay, just some very funny little thing when you change the range, but it does change. Yeah. There we have it. So once again, are we repairing this? We want to know, is the clock running? Yes, it's running. So I have to give them both equal marks in that respect. Both of these tools will tell me if the VRM is running, if the real-time clock crystal is running, if the main 25 megahertz clock is running. They're both telling me that, and they're both telling me that with no hassle. Okay, let's have a look at some more real-life scenarios. Another one then, very common. Does the processor access the BIOS when we power up, or does the GPU access the BIOS? This is often a good indication of what's happening with a motherboard or GPU. Now, the way you would normally check this is by measuring the signal on the chip select, which is pin 1 of the BIOS chip. So we'll just expand that out a little bit. Here you can see this is pin 1 of the main BIOS, pin 1 of the backup BIOS. So we're going to pin 1 of the main BIOS. We'll start the board and see what we get. Okay, so when the motherboard's running, it will have already executed the BIOS code. So the chip select shouldn't actually be doing anything now. It's in fact just going off the scale because I have the sensitivity set too high. Let's go to 1 volt per division. I'm using a ×10 probe, by the way, and the scope is set to ×10. I'll just mention. So we're there, we can see there's a little bit of voltage on there. So we can see there, it's just floating high. Now, when the board accesses the BIOS, I've just switched it off. I'll switch it back on. We should get a series of negative going pulses each time it reads the BIOS. Let's have a look. Yeah, we saw something there. I think I have the time base set too fast, so let's go a bit slower. Try again. Back on. There. Bursts of data pulses, yeah? So we can see it's actually reading that a number of times during the boot up sequence. You saw it there. Let's go off again, and then let's try to capture that. To do this, I press the run stop button, and if you look on the screen down here, it says it's waiting. So we go onto the pin, the chip select pin of the BIOS, and we start the board. And you see it's changed to triggered. So as soon as the voltage came up past the trigger point, it triggered. And we now have a sample, so we can now look around that. Okay, we can expand it, such like. So that's the sample we've taken with this. Let's try the same thing now on the Rigol, and we will compare it again. So I've set it to wait. You can see it on there. Wait, it's waiting for a trigger. We'll start the board, and there we have it. So you see we've captured the signal. Now, what you may not notice, but I'm sure is true, that we're actually capturing more of the signal here. So this has a longer memory, if you like. It stores more of the signal that the other one did. So that's something this does do better. How useful that is in repair work, I guess, really depends on the type of repair that you're doing, but worth mentioning. Okay, so that's one up to the Rigol. How about tracing audio signals and amplifiers and preamplifiers? Well, I think it will come as no surprise that both oscilloscopes are quite capable of doing this, I would think. But we'll just check. So we'll just take an audio signal. It's music, although you can't hear it. And let's see what we have. Well, yeah, you can see something there. Let's go again a bit more sensitivity. And then we have an audio signal. I'll just adjust the time base a little bit, okay? There, okay, so the Rigol is quite happily showing an audio waveform there for music. Now let's try the FNIRSI. And once again, we have an audio waveform displayed. Let's adjust the time base again a little bit. Yeah, and that's doing the same job that the Rigol was again, to be quite honest. No real difference in that. So that brings us to one test left, and that's the switch mode power supply. Can we use the oscilloscope to view the drive waveform to the switch mode transformer? Well, yes we can, but this is where it gets a little bit more interesting maybe. And the reason it gets interesting is because this oscilloscope, powered from its USB style power supply, is isolated from the mains, and I can clip the oscilloscope probe onto hot ground and then measure the waveform on the gate of the output MOSFET. But this one is mains powered. Okay, and this can't do it. I can't connect this to the hot ground of my power supply without either blowing up the power supply or the oscilloscope. Okay, it will not do it. It's not safe. So this is an instance where this one actually can do something this cannot do. Whereas so far we've found situations where they can both do it, but this does it a bit better. High frequencies, long sample rates. But in both those cases, both oscilloscopes can do the job. And in most instances, you can do the repair with both oscilloscopes. But when it comes to the power supplies, it's only this one. Okay, yes, because somebody's going to mention this. This has a maths mode where I can use two scope probes and math function of subtraction to effectively display the waveform, but that is faffing about a little bit, yeah? This one, we just simply use a scope probe and clip to the hot ground on the power supply, and there we have it. Let's have a look. For this last test, I'm going to look at a switch mode power supply. So I want to look at the output from the IC, the one that's driving the primary of the transformer. The easiest place to probe that is actually on this inductor. So we can see this is the positive output of the capacitor, the 320 volts here. And if we look underneath, that actually comes around here to the primary of the transformers. This is the primary winding. And then through this small inductor, the one I just mentioned here, and this is the controller chip. So that small inductor is actually on the output of the controller chip. The problem with this sort of measurement is that the circuit, the measurement, is relative to hot ground, which is the negative end of this capacitor. But the negative end of this capacitor connects directly to the bridge rectifier, that's here, okay? And through the bridge rectifier, it connects to the mains. So this effectively is not isolated from the mains, which means I can't attach any grounded piece of equipment to here. And for that reason, I can't use the Rigol. The Rigol will not enable me to take this measurement. So let's see what the FNIRSI makes of this. To do it, quite simply, I break the big taboo, I connect the ground lead to hot ground, I connect my scope probe to the output of the pulse width modulator chip, the high voltage output on there, okay? And the reason I can break this taboo is because this oscilloscope is mains isolated. I'm using the power supply that came with it, and as FNIRSI say, that is mains isolated. Okay, let's try it. And we're ready to go. So I'll put the power on to our power supply and let's see what happens. Well, you can see we have on the screen 324 volts. It's actually telling us that on the screen, high voltage. And these little pulses you see, this is the switch mode power supply driving the coil. In fact, every so often you saw a large negative pulse. Now the reason it's doing this is because there's no load on this power supply, so it's like an idle state at the moment. It's just sending a drive pulse every so often. So let's see if we can actually capture that. I'll go to single mode, and I've captured it. I have it there on the screen, okay? So we can now have a look at that. We have it captured. Yeah, and you can clearly see there the waveform of the pulse. So we can do that even with a sporadic waveform like this, okay? Now let's switch the power off. I'll put this back onto auto. So we're back into the normal mode there, okay? Just continue trying to capture that. Let's power this off. And you'll see the voltage starts to drop away. You see it's going there, you can see the voltage is coming down, the waveform's coming down. So the power supply is discharging its own capacitors. Yeah, there you go, smaller and smaller. We will see at some point the pulse width modulator stops running. If you also notice the pulses are getting wider as the voltage is getting lower, that's because it's still trying to drive the output voltage, and with less input voltage, it needs to put a wider pulse, okay? Eventually it will give up. We're now down to 10 volts. So that's working quite nicely. As a final test, let's put some load on this power supply and then let's see what happens. To perform this test, you can see I've actually just tagged on a power resistor. So I'm only actually using one of these two. These are 20 ohms each. So I can actually add a 20 ohm load to this. Now this is a 12 volt power supply. So that will give me something like about 0.6 of an amp load. I could have put the two resistors in parallel, giving me a 10 ohm load, which is a bit over an amp, or I can put them in series, giving me 40 ohms. So it's a very handy little load I have here for this sort of work. So I've attached the load to the power supply. Let's power this up again and have a look at the drive waveform to the switch mode transformer. And you can see now this is running, it's running continuously. Yeah, there. Because we have a load. Yeah, this is pulse width modulation. The width of the pulse we see here would vary with the load. So if we increase the load, this would become a wider pulse. This is ringing, which we can see, which is effectively oscillation in the coil after it's switched, okay? So the oscilloscope's showing that. I don't believe the frequency is jittering around because of the oscilloscope. I believe that's the switch mode power supply, just effectively changing the drive slightly. And we can see the frequency it's running at, 60 kilohertz approximately. Okay, so that is pulse width modulation on a switch mode power supply. In action, we can see it, yeah? You probably also noticed just how fast that waveform disappeared when I disconnected the power. That's because there's a load on the power supply, so it will drain the charge in the large capacitor, the one that gives you nasty shocks unless you're careful, because there's a load. This is exactly why if you have a faulty switch mode power supply and it is not running, so therefore there is no load, the capacitor holds a very dangerous charge for a long time. Whereas if the power supply is running, it will discharge it rapidly. Before I sum up this review then, let's just hear what Kerry Wong had to say about this oscilloscope in his review.
You would get much better performance. Personally, I wouldn't touch this scope with a 10-foot pole. It is sad to see that there are so many reviews on the internet actually touting this is a great scope. I for sure would definitely not waste my money on a scope like this. Anyway, let me know what you think about this oscilloscope in the comment.
Okay, so that's Kerry's opinion. Of course, we're all entitled to our opinion. And he also invites people to make their comment on that. So this is what I think about the scope. I guess this is what you've been waiting for. We have it then, the FNIRSI 1014D. Now, you know full well I'm going to challenge what Kerry says about this oscilloscope. I think possibly we are fundamentally coming at this from different directions. But as you've seen in this video, I've taken a number of common situations where you would use an oscilloscope in repair work. These are exactly the same situations I've used previously with other scopes. I haven't selected these situations specifically to suit what this oscilloscope is good at. These are real life situations. And what were the results? Well, clearly for high frequency work, the Rigol, which is an older oscilloscope, is better at that. If you're into radio repair, VHF upwards sort of bands, then there may well be a need for that. And that may be your primary need. And that oscilloscope was outstanding in that area. It performed way above its specifications without using any fancy graphs and whatever. I stuck 225 megahertz into a 50 megahertz scope and it showed me a nice sine wave and told me it was 225 megahertz. What more do I need? Yeah. However, this oscilloscope, when we did the real life tests, worked as well as the Rigol. So voltage regulator module, VRM, pulse width modulator, motherboards, graphics cards, very common use for a scope. One of the times when you want a scope, both did it just as well. Accessing a BIOS, we find this on motherboards and graphics cards again, both did it equally well and both could capture the data equally well. Admittedly, the Rigol would capture a longer piece of data, but I could never think of a situation where you're looking at a chip select on an EEPROM like that you actually need to capture the data. You just want to know if it's being accessed, yeah? If I really wanted to capture the data from an EEPROM, actually I would use a logic analyzer, something that does serial protocol decoding, not a scope. But in this example, both scopes worked equally well. 25 megahertz crystal on a motherboard. One of the fastest clocks I need to work with, one of the fastest ones I want to know, is this running or not? Both scopes did it equally well. Audio waveforms for amplifier and mix repair. Do we have a signal? Both scopes did it equally well. Switch mode power supply. And that's when this one stood out, because this allowed me to take measurements that the Rigol will not. Okay? Yes, I could do it with the Rigol using special methods, but just out of the box to connect it to the board and use it, this did it, the Rigol didn't do it. And we got some very interesting waveforms from that test, again extremely useful in repair work. So I'm not going to say this is the best oscilloscope in the world, but what I do have an issue with is Kerry's opinion on this, that this is junk, that he wouldn't touch it with a 10-foot pole. But to be fair, I like to allow people to have their side of the argument also. So I'm now going to post, when this video is live, onto Kerry's channel. On that video, you will see my post. I'll link it from this one. And I'm going to say, hey Kerry, I invite you to look at this review and I'd like you to explain logically, as I've tried to show logically, why you believe this is a useless piece of equipment. How can it perform all these tasks which are just common parts of normal repair work, if it's rubbish, yeah, surely it can't do it, but it can. And I didn't see any instance when it did it any worse than the Rigol did. In fact, it did it better in the end, okay? So that's my opinion, guys. Yeah, not really a rant, but I do take exception when people call stuff junk when, in my opinion, I can prove it isn't. But at the end of the day, it's up to you guys. This is a sub €200 oscilloscope, okay? There are many other oscilloscopes around. If somebody can come up with a bench scope, which is what it is, like this, for sub 200, or the same price as this, not more, not well for a bit more you can, of course for a bit more you can. For the same or less, if somebody can come up with an oscilloscope bench that will work as well as this one did, then tell me and I'll buy one myself and we'll check that out, okay? That's it, guys. Hope you enjoyed the review. I hope you feel that was a very honest opinion. Personally, I'm very happy to have this. You will see this a lot now. This will be my scope to go for on my videos without a doubt. A lot to do with this clear display, much better than the Rigol, and I think you've seen that in this video. Okay, enough from me. Over to you guys. Comments below. Let us know what you thought. And would you buy one? Ciao for now, guys.